There's a working exploit in the wild right now that gives any unprivileged user on your Linux machine full root access in a single command. And as of this recording, most major Linux distributions do not have a patch for it. No fix, no update waiting in your package manager. Just a publicly available proof of concept script, 732 bytes of code sitting on the open internet that hands an attacker the keys to your entire system. This is not a theoretical risk being discussed in a security research paper. This is a live 0-day that dropped on May 7th, 2026, under circumstances that made an already bad situation significantly worse. And if you're running Linux anywhere, on a desktop, a server, a cloud instance, a container cluster, you need to understand exactly what happened, why it matters, and what you can do right now before patches arrive. The exploit is called Dirty Frag. It is tracked under two CVE identifiers, CVE 2026-43284 and CVE 2026-43500. And it was discovered by security researcher Hyunwoo Kim, who goes by the handle V4Bell in the security community. To understand Dirty Frag fully, you have to understand what came just before it, because this vulnerability does not exist in isolation. It is the second major Linux kernel privilege escalation in the space of a single week, and the two exploits are connected in ways that make the overall situation considerably more alarming than either one would be on its own. The first exploit was called CopyFail, CVE 2026-31431, discovered by the security research firm Theory and disclosed on April 28, 2026. CopyFail exploited a logic flaw in the Linux kernel's AF-ALG cryptographic subsystem, specifically in the algorithm AAD module that handles authenticated encryption and decryption operations. The bug allowed a logical flaw in the AEAD authentication template to cause improper memory handling during in-place decryption, writing 4 bytes of data into protected page cache-backed memory that corresponds to files the kernel has loaded and is actively using. Because set-to-id binaries, programs like the su command that are allowed to run with elevated privileges, are loaded from this same page cache. An attacker, who can corrupt the right 4 bytes in the right location, can modify the in-memory version of a privileged binary without touching the file on disk. The kernel then executes a binary it believes is legitimate, but which has been quietly rewritten in memory. The attacker gets root. What made CopyFail extraordinary was not just what it did, it was how it did it. The exploit is deterministic. It does not rely on a race condition where the attacker has to win a timing game and the exploit might fail half the time before succeeding. It does not require guessing kernel offsets that differ between distributions. It works reliably on the first attempt every time across every major Linux distribution that has shipped since 2017. Researchers describe the bug as the kind of universal, reliable primitive that on the private exploit market would have commanded a price in the range of hundreds of thousands of dollars, somewhere in the neighborhood of what a high-end iOS 0-day would fetch. What made it even more striking was where it came from. An AI system used by Theory's researchers to assist with vulnerability analysis surfaced this bug in approximately 1 hour. That detail produced a wave of discussion in the security community about what it means for the economics of exploit development when AI can compress the discovery timeline for deep kernel logic flaws from months of expert work into a single hour of assisted analysis. To understand where Dirty Frag sits in the history of Linux kernel exploits, you need to know about its older siblings, Dirty Cow and Dirty Pipe. Dirty Cow was disclosed in October 2016 and became one of the most famous Linux vulnerabilities of the decade. It was a race condition in the kernel's copy-on-write mechanism that allowed local privilege escalation on virtually every Linux system in existence at the time. It was fast, it was simple, and it was devastating. But Dirty Cow had one weakness. It relied on winning a race condition, which introduced a degree of timing luck into the exploitation process. It sometimes crashes the kernel on failure. Experienced defenders could detect the spray of failed attempts before a successful one. Dirty Pipe arrived in 2022 and represented a significant evolution. It exploited the Linux kernel's pipe splice functionality to write arbitrary data to read-only files, including set-to-id binaries. It was cleaner than Dirty Cow and did not require a race condition. But Dirty Pipe had its own constraints. Specific restrictions on what data could be written and where in a file the modification could land, which limited its flexibility. CopyFail in 2026 removed those constraints entirely. It is deterministic, it has no race window, it works across kernel configurations without needing per-system offset calculations, and the proof of concept exploit fits in 732 bytes. Dirty Frag is CopyFail's immediate successor in the same bug class, extending the same technique to additional subsystems in a way that invalidates the specific mitigations that CopyFail prompted. CISA, the United States Cybersecurity and Infrastructure Security Agency, added CopyFail to its known exploited vulnerabilities catalog on May 1st, 2026, a week before the public disclosure of Dirty Frag. The agency gave federal civilian agencies a mandatory remediation deadline of May 15th, 2026. Microsoft's threat intelligence team confirmed that CopyFail was being used in active attacks against U.S. think tanks, European manufacturing companies, and cloud infrastructure providers. The scale of exploitation in the wild was documented. Real attacks, real compromised systems, real attackers with root on machines they should not have been able to touch. While all of this was unfolding, Hyunwoo Kim had been working separately on what he would name Dirty Frag. He reported the vulnerability to Linux kernel maintainers on April 30th, 2026, the day before CISA added CopyFail to its KEV catalog. And the plan was a coordinated disclosure that would give distributions time to build and ship patches before any public details were released. That plan broke down on May 7th. An unrelated third party, working independently, reverse engineered the bug chain from a publicly visible kernel fix commit that had been pushed upstream. The kernel fix was already on the surface. Anyone paying close enough attention to the commit history could work backward from the patch to understand what vulnerability it was fixing. And someone did. They published the exploit before the embargo expired, before any distribution had shipped a patched kernel, before any guidance had been formally released. The coordinated disclosure that is supposed to protect users. By synchronizing the moment vulnerability becomes public knowledge with the moment a fix becomes available, that coordination was destroyed. At that point, Kim made the only reasonable decision available. He published the complete Dirty Frag documentation and proof of concept exploit code himself, with the agreement of the Linux distro's security team. His reasoning was explicit. Attackers already had the exploit, so defenders needed it too. Hiding the technical details at that point was not protecting anyone. It was leaving defenders in the dark while attackers operated with full knowledge. The publication note stated plainly, because the embargo has currently been broken, no patch or CVE exists. That sentence, no patch or CVE exists, is the defining fact of the Dirty Frag situation, and it is what makes this moment genuinely different from a typical security disclosure. So what exactly is Dirty Frag, and why is it worse than CopyFail? Dirty Frag chains two separate vulnerabilities. Commit in January 2017, meaning it has been sitting in production Linux kernels for 9 years without detection. The second is the RxRPC page cache, write vulnerability, which exists in the RxRPC protocol implementation introduced in a June 2023 kernel commit, a much newer piece of code, but one that introduced the same fundamental class of problem. The ability to perform in place writes into page cache memory without proper ownership verification. Together, sue binary or the etc. declarator's pasty file, and achieve immediate root privilege escalation. Work, a kernel feature that Ubuntu enables by default, but which some other distributions restrict. The RxRPC module does not ship by default on Red Hat Enterprise Linux or Fedora, but it does on Ubuntu, where it loads automatically. By running both exploit paths in sequence, a single binary achieves root across the entire Linux ecosystem, regardless of which specific distribution-level defenses are in place. No individual mitigation covers both attack paths simultaneously. And critically, here's the point that should alarm anyone who patched their systems against CopyFail and felt secure. The ALGIF-Ed blacklist that was the recommended interim mitigation for CopyFail does not protect against Dirty Frag. The distributions affected read like a complete list of every major Linux platform in production use. Ubuntu is affected. Red Hat Enterprise Linux is affected. CentOS Stream is affected. Fedora is affected. Alma Linux is affected. OpenSUSE Tumbleweed is affected. Rocky Linux is affected. If you are running a mainstream Linux distribution on a kernel shipped since 2017, the XFARM ESP component of Dirty Frag affects you. If you have the RxRPC module loaded, which is the default on Ubuntu and can be optionally installed on RHEL and Fedora, the second exploit path is also available to an attacker. The blast radius of this vulnerability in terms of affected systems is effectively the entire Linux ecosystem in active production use globally. Platform, a Kubernetes cluster, or any system where multiple users have shell access or where containers share an underlying kernel, Dirty Frag is not just a local privilege escalation. It is a container escape. An attacker with code execution inside a container, if the underlying kernel is vulnerable, can use Dirty Frag to break out of the container namespace entirely and gain root on the host system. That means one compromised tenant can own the entire host and every other tenant on that host alongside it. Cloud providers scrambled immediately after the disclosure. This is exactly the nightmare scenario for multi-tenant infrastructure. What is notable is what did not break under Dirty Frag. AWS Lambda and AWS Fargate, which run workloads on Firecracker micro VMs, separate kernel instances per tenant rather than shared kernels, were not affected. Cloudflare workers, which run on V8, isolates entirely outside a traditional Linux kernel threat model, were not affected. Google's gvisor, which interposes a user space kernel between the workload and the host, was not affected. The pattern is entirely consistent. The isolation boundaries that are held against dirty Frag are the ones that do not share a kernel between untrusted workloads. The boundaries that failed, standard Linux containers using namespaces and C groups on a shared kernel, are also the ones that the majority of production Kubernetes deployments use by default. This is not a new finding. Security researchers have been arguing for years that the shared kernel container model provides weaker isolation guarantees than hypervisor-based virtualization, and that any serious kernel vulnerability converts a container escape risk from theoretical to trivially exploitable. Dirty Frag is the latest demonstration that makes this argument concrete and immediate rather than abstract and future-facing. The shared kernel model that makes containers efficient is also what makes a kernel privilege escalate into a platform-wide emergency rather than a single system incident. While patches were not available at the time of disclosure, the upstream kernel developers began merging fixes rapidly after the embargo broke. Alma Linux moved quickly, pushing patched kernels into testing repositories within hours of the public disclosure, then rolling them into production mirrors on May 8th. The combined kernel addressing both CVE 2026-43284 and CVE 2026-43500 reached Alma Linux production repositories on the afternoon of May 8th. Other distributions began publishing security advisories and accelerating their backporting of the upstream fixes. The situation that existed at the moment of disclosure, no patch, working exploit in the wild, was moving toward resolution, but the window during which every major Linux system was exposed with no fix available was real, and for any system actively targeted in that window, the damage was already done. For anyone running an affected system right now, there are two layers of response. The first is the interim mitigation while patches reach your distribution. Blacklisting the vulnerable kernel modules prevents the exploit from loading the code paths it depends on. The modules to blacklist are ESP4, ESP6, and RxRPC. Adding these to a mod probe configuration file and removing any already loaded instances from the running kernel closes both attack paths. The command to do this looks straightforward. A printf to write 3 blacklist entries into the mod probe configuration directory, followed by rommodi to unload any already loaded instances. The trade-off is real. Blacklisting ESP4 and ESP6 disables IPsec ESP transport mode, which is used in certain VPN configurations. Organizations running IPsec VPN tunnels face a genuine dilemma: lose VPN connectivity or leave systems vulnerable. For most desktop and general-purpose server environments, where IPsec VPN is not in active use, the blacklisting approach is safe and should be applied immediately. There is also a dimension of this situation that gets less attention than the technical details, but matters enormously for the people managing real systems. The emotional and organizational cost of a 0 day with no patch. When a vulnerability has a patch available, the response is structured. Assess, prioritize, schedule maintenance window, apply, verify, move on. When a 0 day is live with no patch, that structure collapses. You are in a continuous state of elevated alert with no clear resolution timeline. Every hour that passes is an hour of exposure you cannot close with the normal tools. The only options are workarounds that may break functionality and waiting. For administrators managing hundreds or thousands of Linux systems, the waiting period under active exploitation pressure is genuinely exhausting in a way that standard patch management is not. The Dirty Frag disclosure, arriving 1 week after CopyFail and before CopyFail had even been fully patched across all affected systems, compressed that pressure into a window that tested the organizational resilience of security teams across the industry. The second layer is applying the distribution-provided kernel update as soon as it is available for your system. The upstream fix has been merged. The backporting work is underway across distributions. Running sudo apt update and sudo apt upgrade on Ubuntu, or sudo dnf upgrade on Fedora and RHEL-based systems, and then rebooting to load the new kernel. This is what closes the vulnerability definitively. The module blacklist is a bridge to reach the patch, not a permanent replacement for it. There's a larger story embedded in these two back-to-back exploits that is worth sitting with. CopyFail was found by an AI system in approximately 1 hour. Dirty Frag followed 1 week later, extending the same vulnerability class to a different subsystem using techniques that the CopyFail disclosure effectively made visible. The security research community is openly discussing what this pattern means for the future of kernel vulnerability discovery. The argument made by analysts at BugCrowd is direct and unsettling. The assumption built into enterprise patch cycles, vulnerability budgets, and CVE prioritization models is that finding a kernel-grade privilege escalation is expensive, so the supply of new ones is roughly bounded by how many expert humans are available to look for them. CopyFail breaks that assumption. If AI-assisted analysis can surface a universal, reliable, no-race condition kernel LPE in an hour of work, the cost of finding these vulnerabilities has dropped by an order of magnitude. The defender's window between when a critical bug is discoverable and when it is discovered has shrunk in ways that traditional patch cycle planning does not account for. The average enterprise Linux environment runs a 30-day patch cycle. The average time from public vulnerability disclosure to active exploitation in the wild is 15 days. For CopyFail, CISA added it to the known exploited vulnerabilities catalog, confirming real-world OS attacks, while Dirty Frag was already reported to maintainers and awaiting coordinated disclosure. The 2-week gap between discovery and the mandatory remediation deadline that CISA set was already optimistic. For Dirty Frag, the embargo broke before any patch existed. Federal agencies were ordered to patch by May 15th for a vulnerability that had no patches when the order was issued. That is not a compliance problem. It is a structural problem with how the entire ecosystem handles disclosure timing, embargo management, and the race between defenders building patches and third parties, reverse engineering fixes from kernel commits. What Dirty Frag makes undeniable is that treating Linux kernel security as a background concern, something handled by whoever manages the updates, patched on the next maintenance cycle, reviewed when convenient, is no longer a defensible posture. The kernel is not stable infrastructure between patches. It is an active attack surface where exploits can materialize from public commit history, where AI tools accelerate discovery timelines, where a single bug sitting quietly in IPsec code since 2017 can become a universal root shell at any moment. The open source model means the fixes, when they come, are fast and transparent. But it also means that anyone watching the kernel mailing list can race against distribution maintainers to get there first. The embargo broke. The exploit shipped. Right now, somewhere, Dirty Frag is being used on a system whose administrator has not yet seen the story. Check your kernel version. Apply the blacklist, then apply the patch. In that order, today. For desktop Linux users, the risk level is lower than for servers and cloud environments, but it is not zero. A local privilege escalation exploit requires an attacker to already have a local user account or code execution on your machine. On a single user desktop that you control, the attack surface is narrower, but malware, browser exploits, or compromised applications that achieve code execution in your user context can all serve as the entry point for an escalation attack. The answer for desktop users is the same as for everyone else. Check whether your distribution has pushed the patched kernel, install it, and reboot. Most major distributions were moving quickly to backport the upstream fixes, and the window of exposure for desktop users who keep their systems updated should be measured in days rather than weeks. For administrators running servers or cloud infrastructure, the urgency is higher and the response needs to be more structured. Audit every Linux system in your environment for kernel versions. Identify which ones have the patched kernel available and prioritize rebooting into it. For systems where the patched kernel has not yet arrived, apply the module blacklist immediately and document which systems are running in a mitigated but unpatched state. Monitor audit D logs for exploitation attempts. The exploit's page cache write pattern is visible in kernel audit output if auditing is enabled, and revisit your isolation model for multi-tenant workloads. If shared kernel containers are your primary isolation boundary for untrusted code, Dirty Frag is the argument you bring to the architectural review that justifies the migration to micro-VM or hardware-level isolation that you may have been putting off. The name Dirty Frag joins a list that includes Dirty Cow, Dirty Pipe, and CopyFail, a lineage of page cache manipulation bugs that researchers keep finding in code that has been running on hundreds of millions of Linux systems for years without anyone noticing. Each one builds on the understanding produced by the last. Each one is more refined, more reliable, and more broadly applicable than what came before. The pattern suggests that this class of vulnerability is not exhausted, that there are more instances of improper page cache write behavior sitting in kernel subsystems that have not yet been audited with the kind of systematic attention that AI-assisted research can now apply. The Linux kernel is open source, which means the community will find these bugs and fix them faster than any closed source vendor could. But open source also means that anyone motivated to look can see the same code and the same fix commits that the defenders are working from. The race is real. And right now, with Dirty Frag in the wild and patches still arriving at millions of systems, it is a race that not everyone is going to win.